So today we will discuss about multiple instance learning in medical imaging. So these are the contents of today's lecture. First of all, we will discuss about multiple instance learning, what it is, then why we use MIL in medical imaging, then some theoretical framework, key MIL approaches, and then lastly we will discuss some case studies. So actually multiple instance learning is a type of weakly supervised learning. You all know about supervised learning, semi-supervised learning, weakly supervised learning, and this multiple instance learning is a type of weakly supervised learning in which we have loosely labels or incomplete labels. In order to tackle these kind of challenges in medical imaging, we use multiple instance learning, where we have multiple instances but we don't have tightly labels. For example, we have a data point and we have some labels related to that data. In traditional supervised learning, we have like this. For example, this is a data point x1, x2, x3. So corresponding to each data point, we have some labels. For example, we say that this is cat, dog. Here you can see, for example, this is a whole slide image, and we have one label for this whole slide. And in MIL, we consider this whole slide as a bag. For example, we consider this whole slide as a bag, and we have one label for this one. And when we are applying MIL, we have to make patches. For example, this is a very big image, and we need to patch all these whole tissue and whole slide images into small patches of smaller size. For example, 256 or 224 or 256. It depends upon your criteria, what you want to keep the size of the patches. So we need to make patches of the whole slide image, and in this whole slide, this is a big image, and only this area is tumor area, and we don't know which page, we don't know the label of all the instances in this whole slide image, and we give one label to this whole bag or whole slide image. And based on this label, for example, we give this whole slide as a positive. Based on this label, it detects the tumor area in the whole slide image. So if I show you how big is a whole slide images, this is so big. How zoom you can do it like this, you can see. So for this whole slide, in multiple instance learning, we give one label for the whole bag. You can see that a bag is labeled positive if at least one instance is in it is positive. For example, here you can see there are different scenarios. In this one, we have 2 instances with positive and 3 with negative. Here 3 with positive, 2 with. So at least one must be positive for a bag to be positive. And negative bag contains all the negative instances. For example, tumor or non-tumor. Non-tumor, we say that is negative bag, and in tumor at least one instance should be positive. For example, in this, for example, this area is tumor, so we call this slide as a positive bag. So multiple instance learning versus traditional supervised learning. In traditional supervised learning, as I mentioned here, every data point has its corresponding labels. For example, x1, y1, x2, y2. But in multiple instance learning, we have a bag, and for the bag we have a label. I guess you understood this concept. And then why multiple instance learning for medical imaging? So as I showed you that whole slide image is extremely big, and its size is around, for example, 100,000 into 100,000 pixels. So it is very difficult for the pathologist or the radiologist or the physicians to annotate the area in the whole slide. So there is a need of such kind of systems or algorithm that can detect the tumor area in the whole slide. And the tumor area is a little bit, not too much big. So in order to tackle such kind of problems in medical imaging, this methodology has been introduced. And what it does, manually annotation is time consuming and expensive, and with the MIL only we need slide level labeling. Based on that slide level labeling, we go into the tissue area and finds out the area inside the tissue, the tumor area. So in how it benefits us, it doesn't need manual annotation. No additional annotation burdens on clinicians, can highlight suspicious regions for the review and accelerate analysis of the large dataset. And it can detect the tumor area in the whole slide image and identify pathological regions without pixel level annotation. So the standard MIL assumption, these are the same things, but I have shown with some formula. For example, B considered as a bag, and it contains these instances. For example, x1, x2, and xn or m. This shows the patches inside that whole slide. And if the whole slide contains at least one positive or tumor area, it means this is positive bag, and for the negative bag, all the instances should be negative, and it should be normal, or there must not be any kind of tumor area or tumor cell in that whole slide image. So mathematically it can be represented like this formula. And collective assumptions, all instances contribute to the bag level. When we are dealing with whole slide images and multiple instance learning, we calculate the score for each patches, and each page contributes for the slide level labeling of the images and average of instance prediction, and we assign some value and some threshold value for the prediction of positive instance and the negative instance. So these are the approaches, well-known approaches in multiple instance learning. First one is instance space approach. It learns an instance level classifier, aggregate instance prediction to get bag prediction, in which it goes inside to the, for example, so it goes here. For example, we label it as a positive bag, and when we apply the algorithm, it goes into this page area and it finds the score of each page, and every page contributes to the overall level of this whole slide image, and it contributes for the labeling of the whole slide. Because every page has some kind of score, and based on those score, the pseudo label inside the algorithm decides which kind of label should be which kind of label should be assigned to that label for that bag. Then we have Then we have backspace approach, in which we tries to find the similarity between different kind of bakes and apply standard classifiers using this similarity approach. And at the end, we have embedded space approach, in which we transform bakes into fixed dimensional feature vectors, apply standard classifier on these vectors. And in deep learning MIL method, we have mainly three kinds of deep learning methods in MIL, in which we apply max pooling, mean pooling, and attention-based pooling. These are well-known approaches used in deep learning for multiple instance learning. So attention-based MIL, what it does, it learns to focus on the important instance and assign different weights to different instance, and enables interpretability by highlighting important region. So to apply this attention-based MIL, first of all, we make patches of the whole slide image. Then we extract the features while using any kind of CNN architecture, and we calculate the score for each page. After that, we apply some weighted average for each instance, and at the end we use some classifier for the classification of the different classes. So digital pathology application. In digital pathology, we can use it for tumor grading, metastasis detection, and survival prediction and biomarker prediction. We are using it for metastasis detection in our digital pathology project. So this is the overall workflow, how it works. And first, we have whole slide image, we make patches, then we extract the features from the patches, and then we apply MIL aggregator, and after that the slide level prediction. So we take an example. For example, I have choose this paper, which is data efficient and weakly supervised computational pathology on whole slide image. And this is actually a clustering constraint attention multiple instance learning, which is very famous, one of the famous approaches in multiple instance learning, CLAIM. It is deep learning based weakly supervised approach, and it works on attention based mechanism. It is efficient and fast, because previously we were using some other approaches as well, for example MRN, DTFD, and dual stream networks, but those approaches were slow and they were taking too much time. Then we use this approach in our experiment for the prediction of metastasis and non-metastasis, and we observed in our experiment that it is very fast and also have good performance, because previously those approaches functions based on the pixel space, but in this approach it functions and it works in low dimensional feature space. We only save the features, not the pixel and images. Because of this functionality, it is faster and also efficient. And it can also be used for multi-class classification as well, and it is capable of distinguishing between tumor and adjacent normal tissues. So this is the architecture of CLAIM approach. We have whole slide. As I show you one example of whole slide. Here they have shown, for example, for this slide, they have it is 89,000 into 79,000 pixels. In our scenario, that was example from our data that has around about 147,000 pixels. So this is whole slide image, and first of all we extract the tissue area from the whole slide. Actually whole slide image contains these areas as well, background as well. We extract only the tissue area from the whole slide. Then we convert RGB into HSV, because this HSV space is more reliable while implementing your algorithm, and it makes the algorithm faster as well. And then we make patches of these tissue area, only these, because we have already removed the background and only we have tissue area. Then we apply patching and we make patches according to our requirement, and then we have different kind of patches. For example, it depends upon the size of the image. If the size of whole slide image is big, then the number of patches will also increase. For example, in our case, for one image we have more than 1500 and sometimes 20,000 to 2000 patches. So it depends upon the size of your whole slide. Then we apply the feature extractor. For example, in this case they are using ResNet 50. While using ResNet 50 architecture, we extract the features and we convert the features into low dimensional, because if we for example, if the size of the image is 256 by 256, it is too much, and we reduce this to 1024 dimension, and we use those 1024 dimensional vectors for the MIL training. Here we use different attention networks. For example, here they have 3 classes or multiple classes. Based on each class, there are different attention branch, and it finds the score for each class, and at the end we have the attention map of the whole slide image. For example, this area here shows that this area has high attention score, and based on this score, the color of this area is red, and compared to these pages have low attention score. Here actually this is the internal mechanism of this network. Here each page has we rank the score of each page here, and it classifies between the positive and the negative instance of the pages of the bag, and based on the score of each page, it classifies whether it is positive or negative instance of the bag. So starting from the data pre-processing, these are the different parameters of the segmentation. For example, segmentation, we can set the segmentation level, at which level we want to segment out the tissue, and it shows S threshold shows the segmentation threshold. For example, if you increase the number of this S threshold, then the background, there will be more background. If you keep the threshold value low, then it will segment out the tissue area more. So these are different kind of parameters of segmentation you can see here, and we make patches of 256 by 256. And these are other parameters. For example, we have AT, area filter threshold for tissue, and AH, area filter threshold for holes, because sometimes in whole slide images there are some holes as well, so we want to fix how much area of the hole should be. If it is too big, then we have to consider. If it is small, then we just ignore. So these are different parameters. And here, for example, if you want to apply this, so this directory contains the whole slide images. You can see data directory, it contains the whole slide, and when we run this, this code will segment out and make patches and shows the contours and different kind of functionalities with this code. Here you can see stitching, segmentation and patching, and you have different parameters here. From here you can change the parameters of the segmentation and patching, and with the help of this code and this whole slide image code, you can segment out and you can make patches of the whole slide image. So when you run this create patching code, it will generate your results here, result directory. In result directory you have these mask, patches and stitches. So patches are in this form, for example H5 format. Previously in the other approaches we were having the patches into, for example we have some images in this form, for example images, maybe PNG form or JPG form, but in this case we are saving the coordinates of the patches, actually coordinates of the patches in this H5 format, because this is efficient and fast, so that we can easily retrieve only the pixels, not the whole images. For example, previously we were making patches of 2 to 4, 2 to 4. So it takes too much memory as well as it takes time for retrieval. Therefore this approach is more efficient, and it saves the pages in this format, H5 format and PT format. So once we run the patching code, it will generate these file and folders. For example, this it generates this information. For example, for this slide, 0 means it has been processed complete. If it shows 1, it means that this slide has not been processed. These are the different parameters as we have shown there. Different, for example, the segmentation level is 3, threshold S threshold value is 12, and other parameters here. We can check on which level the slide has been extracted and had been patches. Sometimes based on the slide we need to change these parameters according to the size of, for example, some slides are very big, some slides are very small, so we make individually. For example, in this case we have taken this segmentation level as 3. For this slide, for example, we have made 2. So we need to check and we have to change the values so that we can segment out the whole slide image properly. So once we complete it and we are done with the segmentation and patching, we need to extract the features. So the format I have shown here, for example, mask, patches, stitches, and the result directories are like this. And mask, you can see here, we are doing masking like this. For example, tissue segmentation like this. And after that, here are the examples I have just shown you. Then feature extraction. In feature extraction, we read metadata from the CSV listing slide labels as shown here. We use the same, for example, this CSV file for the patching as well. Based on the information contained in this file, we extract the features from the patches. And here applies deep learning model which is ResNet 50 to extract the features from each pages. Save the feature in both H5 and PT format for later use. And after that, we have actually these H5 files contain the coordinates of the pages, and we reduce it to 1024 feature dimension. And the format, the data format is like this. For example, we have H5 files, PT files, and H5 file contains the name of the slides, different name of slides, and we also have the same in the PT format as well. I will show later. First of all, I want to go with this one, then I will show. So then we have feature extraction I just explained. For example, the size of the pages is 256 by 256. Then we apply this formula for the dimensionality reduction, and we convert the features into 1024 embeddings. And after that, for the training, we need to make some changes there. For example, we need to we extract the features, and we have to put those H5 files in the under this data root directory, as well as PT files here. And we also need to provide the labels of the slides in CSV file format. And in CSV file, we have 3 columns. For example, case ID, slide ID, and labels. I will show later. Then attention based deep MIL architecture. Then we apply this approach, in which attention module with learnable parameters and attention mechanism is introduced to ascertain the importance of the different features acquired from different pages, while applying this formula, where W1 and W2 represents the transformation matrices, tanh and sigmoid. These are the activation functions we use in this approach. Here, after that, we make clustering. For example, the pages having higher score, we set some values. For example, K value, maybe 10 or 20, depends upon the situation. We categorize into highly positive and highly negative, and make rankings of the pages. And based on the score of each pages, it shows, for example, if the score is very high, it shows the color with the red color, and if the values are low, then it shows with blue color. And at the end, we apply the we try to minimize the loss and find the class prediction. So it combines page level representation for each class with slide level representation using attention based pooling function. Actually, we are using attention based pooling function. And the attention networks predicts different sets of attention score corresponding to the number of classes in a classification task. It gives the network the ability to categorically learn which morphological feature should be regarded as positive disease feature versus disease negative feature for each class, as I explained you. So here is the overall workflow of the algorithm. For example, we have data set. I have shown the directory having the whole stack images. Then we have model, and we have to set the base size so that computationally efficient. First, we have WSI, and we have to make the pages of the whole slide images, and the pages are x1, x2, and xk. Then we compute the feature for each pages, and after that we apply dimensionality reduction, and we convert the whole slide into the pages into 1024 embeddings. After that, we find the attention score for each page. Then we aggregate all those scores, and based on those score, it internally also have some pseudo label for the each bag, and it predicts the slide label at the end. And in this way we train the model and we minimize the loss and find the prediction. So once we're done with the training and we can check the results here. We have different kind of folds. For example, we have 10 folds. For each fold we can generate the weights for each fold, and we use these fold for the heat map generation. I will show you later. Here the organization of heat map, data organization. In the heat map generation process, we have these kind of folders. This folder contains the config template in which we need to put the weights which has highest score in this file, and in this file contains two folders, checkpoints and the slides, and we have to get the checkpoints from the results folder and we have to put it here. And this folder contains the slides which you want to check whether it is metastasis or non-metastasis. We have to put in this folder, and this folder contains the heat map, for example in H5 format, PNG format, JPG format and others, and we can check the results here. This is the attention map at the end. For example, the model has predicted this area is the tumor area, and here then we check with the pathologist. For example, this area has been annotated by the pathologist and this area has been predicted by the model, MIL model. So in this way it works, and it helpful for the pathologist to use this kind of system in their clinical use. So I will show here how can we, for example here we were here. Once we run this, for example create patching code, we will get the results here. Once we get the results here, for example we have patches in this folder, then we need to copy this folder and we have to put it here. For example here, this is the same folder which we have generated with the use of that code, segmentation and patching code, create patching code. Once we run, for example this create patch code, feature extraction code. This is the feature extraction code. While using this code, we can extract the features from the patches. You can see from here we can change different architecture. Here they have used 50, but in our case we have used uni, and here you can also use different kind of other architectures as well. So we run this code and generate the features, and the features are here in H5 file format and PT5 file format. After that we copy these two files here. Here you can see in in this folder we have to keep these the features we have extracted, we have to put it here, H5 files and PT file. Then we have to copy this PT file into this folder so that we can train the model efficiently, because this is the file organization given by them. You have to follow this to run this MIL approach. After that you have to give some information here. For example, this is for binary class classification, we have CSV file in which we have slide ID and we have label. For example, in our case we have meta and non-meta, we have represented like this. You have to put like this, and it can also be implemented for subtyping as well, for multi-class classification. Once then you have to run the main code. It will generate the test AUC, test accuracy, validation AUC, and validation accuracy. And here you can find different kind of parameters here. For example, ADAM optimizer, SGD, and we can also change with single branch and multi-branch, and all the informations are here. We can tune the model while changing these parameters. And once we run this, then we have results here. These are the different checkpoints. For example, for zero fold we have checkpoints, for 1 for each folder. For each we have different 10-fold cross validation, right? So for each fold we have respective checkpoints, and in this file you can find the accuracy or whatever. You can see here, you can generate the results here in this format. Checkpoints here in this folder. For example, you have to visualize which fold has higher score, then you have to put that corresponding checkpoint in this folder. You have to put here, then you have to change the name in the YML file. In this file you have to change. For example, here you have to change here. Then you have to put the information of the whole slide, for example name of the whole slide, and also you can give any label to your whole slide. For example, if you want to check the prediction of the whole slide, whether it is meta or non-meta, you just randomly put any label to this slide. Then after that, when you run the code, you will generate the heat map in this folder. For example, here in this folder, only one example, you can see the attention map. Here like this, the red area shows that this is tumor area and the blue area shows that this is normal area. So based on the attention score, it is showing different colors to different patches. In this way it works. So if you have any question, you can ask.